Okay, so so I have to kind of get started just because we got this thing taped here. All right, so I'm opening up right now on the screen in class the PowerPoint. So for those of you at home, your screen is already showing, but the screen in class is not, and I'm getting it to show right now. Okay, so hopefully this works. It very well may not, and I may not have to do this again as far as the videoing goes, but it may work. All right, so Chapter 7 is on demand estimation and forecasting. So as you guys know, we skipped Chapter 5, right? We went from Chapter 4 to Chapter 6. We skipped Chapter 5. I can kind of give you a real quick synopsis of what Chapter 5 dealt with. It kind of dealt with consumers. It was very theoretical. They talk about stuff called utility curves and how consumers are trying to maximize their utility, which is happiness, right? Subject to income and stuff like that. So one of the reasons we skipped that was it starts to go into things called isoquants, and it gets further into those elements in Chapter 9. So we're only going to deal with a small sliver of Chapter 9, okay? So we're actually going to go through, hopefully, kind of 2 chapters and like a little tiny slice of Chapter 9. So 7, 8, and a little tiny bit of Chapter 9 tonight. And believe it or not, this shouldn't take terribly long, so it should be pretty efficient. All right, so last week we talked in Chapter 6 about demand elasticity. And in Chapter 4, we talked about estimation. So Chapter 4, we dealt with a lot of statistics and whatnot. And up until now, you probably thought of demand as being a kind of theoretical subject. But this here is where we start to actually make it quantifiable. Real life quantifiable, meaning actually estimate it and potentially forecast it. So we've discussed the need for models. Now we put our model, which is the demand model, to work. The preface for the chapter looks something like this. Pricing and production decisions are going to come down to information about demand for your product. So we're turning theory into statistics here. Knowing how your product or service responds to general economic or demographic fluctuations is important. So demand for takeout may increase during recessions. That might not make sense right off the bat because you think, okay, people don't have as much money. But on the other hand, it may make sense because maybe people are trying to keep their jobs more so or something like that. Demand may be altered by population shifts. I was reading an article about where the labor force is going to grow the most over the course of the next 20 years. It's interesting because pretty much the entire Northeast is not where it's going. It's going down southeast, kind of actually towards the west too. Might be that. Yeah, Midwest. Actually, you're right. North Dakota was doing quite well. But yeah, what I thought was interesting is I kind of consider Northeast to not necessarily be a place I would assume lots of people would be leaving. But according to this, that should be expected. But that's something that I think is important to note because if you're, a manager, or if you end up being like a Fortune 500 CEO, you should probably know where demographics are shifting so that you can sell to those demographics. So empirical knowledge of demand is needed, and in order to obtain empirical knowledge of demand, the first thing we need is data. So we're going to start by asking how can we obtain data that we can use to kind of create demand or an empirical version of demand. The first one that the text talks about is consumer interviews. And these can range from stopping shoppers to speak with them to administering detailed questionnaires. This is really giving kind of this part of it is giving a brief overview of demand estimation. and we're going to kind of just simply overview it. But there are some holes in what they talk about here. Consumer interviews is one of the aspects that they discuss. There are some things that they kind of leave out, and we'll talk a little bit about them. What are some of the problems with consumer interviews? Well, the first problem is selection of a representative sample, which is a sample which is usually random, having characteristics that accurately reflect the population as a whole. So let me ask you guys this. If you are calling for a representative sample for your product and you call people on home phones, do you think that that would provide you with a representative sample? Why?
Because you don't know their demographic. You don't know how many children they have, what nationality they are, what their income is. You don't know what their house, type of development they live in.
Right.
Sort of thing.
Yeah, I
Their
think that that's right.
economic status.
Yeah, generally speaking, you're going to want to know, okay, you have an idea of who's purchasing your products, their demographics. You want your sample to represent that, and most likely, I have a home phone, but I think I'm in the minority these days. So I think that your sample might be thrown off by having trying to just reach people through home phones. Another thing to think about is response bias. And this is the difference between responses given by an individual to a hypothetical question and the action the individual takes when the situation actually occurs. So today, at my day job, we were talking about this CE credits for this designation that's given from where I work. Think of it like a CPA. And all of a sudden with this, it's called the CPCU, they decided that they'd like to consider allowing individuals to pursue continuing education. Let me ask you a question. If you were going for a designation and you heard that all of a sudden you're going to have to not only finish the designation but then have to do continuing education for the rest of your life to keep the designation, would you be more or less likely to continue to pursue that? Less likely, right? So anyway, they were talking about today, and they were like, well, we ran a survey, and we found that 28% might stop the program altogether if we do this. But then we reached out to those 28%, and we asked them, if you look at this model of how we would do this, would you change your answer? And to me, I started kind of laughing to myself because you can't do that. You can't go back to the people you surveyed and then ask them, if we change something, would your answer differ? Of course it's going to differ. That's a response bias. They know that you wanted them to answer a particular way. They're upset at you for answering one way. Of course you're going to say, oh yeah, but when it comes down to it, would you actually finish? Maybe not. So I think that that's something to think about, and it happens it happened today to me. So I'm sure you might see something like that in the future. Another problem is the inability for the respondent to answer accurately. Sometimes you just don't necessarily know the right answer. Another type of method to gather data for demand is market studies or experiments. And market studies attempt to hold everything constant during the study except for the price of the good. Lab experiments are going to use volunteers to simulate actual buying conditions. These experiments or field experiments are going to observe actual behavior of consumers. Have you guys ever seen one of the shopping type experiments before, where you have consumer shopping behavior and trying to monitor what the consumers do? They actually do these things. I think some of these are a little dated because there's some new ways to go about it too. I would say something like observational data is something that's left out in your textbook. And something we talked about last week when we talked about Target. They're actually observing your behavior with Target. And that's not really included here in depth. With those cards, they can monitor what you're doing and therefore obtain more information on you. So that's another way to gather data that's not necessarily mentioned here. Okay, so empirical demand functions. demand equations are derived from actual market data here, and they will be useful making pricing and production decisions. So basically what we're doing is we're taking the theory of demand and we're gathering data to try to create our own demand curve. A empirical demand function looks something like this. In linear form, an empirical demand function can be specified as Q, which is our quantity demanded, is equal to A, which is our intercept, plus B, which is the slope of P, which is our price, plus C, which is the slope of M, which is your income, plus D, which is the price of related goods. So let's back up. This is something we talked about. I know I'm seeing some of the students in here kind of put their heads down. They're like, oh no. Okay, so we did talk a little bit about this in chapter, what is it, 2? It looked something similar to that. Do you remember that equation where we had quantity demanded on the left-hand side, and then we had A plus B, and then it did have a P, and then it had plus C, and then it was M again. That was for income. And then it was, I believe it did even go to plus D times PR. And it's the exact same thing that we saw there. So this is not new, except that they threw out some of the elements all the way to the end. So this is not necessarily too new for you, but in some ways, you know, this thing is still kind of new for us as a class. So it's good to kind of go through it a little slowly. Just to reiterate, P here is our price of our good in question. M is your income. And price of the related good is that PR, okay? So if you think of, you might be like, what's the price of a related good? Well, it could be something like chips and dip or something like that. So if the price of the dip goes up, what's going to happen to your quantity demanded for chips, that sort of thing. Okay, let's get a little bit more in depth in this. We did talk about some of this stuff before, but it might look a little different now. So let's start by saying, what is B? B is our slope. It's the slope of P, okay? Remember what our slope equation was? It was, you know, your change, right? Your change, your rise over run. In this case, considering the Q is on the left-hand side, that's our rise, and our run is the P. So the B is going to have change in Q over change in P. So you can predict that C is going to be equal to your change in Q over your change in M, and D is going to be equal to your change in Q over your change in your price of related goods. So let's stop here and let's ask ourselves, what exactly is this even saying? Why are they doing this? Just to confuse you? No. They are trying to ask questions like this. If I raise my price, what's going to happen to the quantity demanded? That's the first one. B is going to tell you that. So how much can I raise my price and how is that going to affect my quantity demanded? That's why they have the little delta symbols. It's saying change your price. How much is that going to change your quantity demanded? That's what the B is telling you. The C is telling you if incomes increase or decrease, how is that going to affect my quantity demanded for my product? So keep in mind, this is kind of looking at things from a different perspective. It's kind of looking at more almost from the producer's perspective. And then D is asking, if a price of a related good changes, how is that going to affect my quantity demanded? So once again, chips and dip example, if the price of dip increases, how is that going to affect the quantity demanded for chips? So these are all reasonable questions that a producer might be asking, and that's why they might want to empirically estimate their demand function. All right, so let's talk a little bit about the expected signs we see here. B is expected to be negative. Why do you think B is expected to be negative? So that's saying that there's a negative relationship between price and quantity demanded. Makes sense, right? So if the water that I purchased today was priced higher, most likely quantity demanded for that water would go down. C is going to show you that the expected sign there is positive. This is stuff we've already covered before. It's just a reiteration of it. If incomes increase, you should expect quantity demanded to go up. And if incomes decrease, you should expect quantity demanded to go down. That's for normal goods. Now, we talked about inferior goods before. I tend to use the example of, kind of natty light beer or whatever. But you probably have an example that you know of. Maybe, you buy the Acme brand potato chips or something like that. As your income increases, you might not buy that particular brand anymore. And that might be considered an inferior good. D is positive for substitutes and negative for complements. So let's talk a little bit about this. Pepsi and Coke. So if the price of the related good is you're looking at the quantity demanded for Pepsi, and you're looking at the price of Coke. If price of Coke goes up, what would happen to the quantity demanded for Pepsi? It would go up. That's why it says it's positive for substitutes. How about negative for complements? That's again like the chips and dip, like I said before. If the price of the dip goes up, most likely the demand for chips might go down. And that's why there's a negative relationship there. Okay? Okay, so estimated elasticities of demand are computed as, sorry about this, bear with me for a second. Here, we have our estimated elasticity of demand computed as our B hat over, or multiplied by P times Q. This might seem really confusing. You might feel like, where is this B hat coming from? But let me continue on first. Then look, the elasticity of income is computed as C hat times M times over Q. And finally, the elasticity, which is called the cross-price elasticity of the related good, is D hat, which just has the price of the related good over the quantity demanded. So let's back up and let's talk about this a little bit. What is B? Right, it's the slope, which was the change in what? Change in Q over the change in P. Okay, so just follow this equation. I can't write it down normally under certain circumstances. I'd write this down, but follow this with me for a second. Change in Q over change in P times P over Q. Does that ring a bell as an equation? You just went through that, right? And now the next one underneath it, think of it like this. Change in Q over our change in M times M over Q. It's very similar, right? We're just substituting the M in now, which is our income. And then finally, D would be your change in Q over your change in the price of the related good times the price of the related good over Q. So the point being, if we go back here and kind of point to the top, that top equation, Q equals A plus B times P plus C times M plus D times price of the related good. That B is our slope, okay? Right? That B is our slope. And in order to get the elasticity, all you need to do to that slope is multiply it by P over Q. And to get the elasticity of M, all you need to do is take that slope of that C and multiply that times M over Q. And for D, to get the elasticity of D, all you need to do is take that D and multiply it by PR over Q. Okay? Just like we did in the last chapter, in chapter 6. It's just extending that theory on. Okay. All right, we're moving on for the demand of a price setter, or for a price setter, I should say. Before we get into this, what is a price setter? Do you guys have any idea what you think a price setter might be? Go ahead. Exactly. Exactly. Price takers would be, we haven't really gotten into this yet, but actually we did a little bit of in chapter 1, would be kind of like more farmer type products like pumpkins we used and that sort of thing, where steak, what's for dinner. They're basically you put it out there, you take the market price. Price setters set the market price. So to estimate the demand function for a price setting firm, there are several steps included. The first step is to specify the price setting firm's demand function. Okay? So kind of specify it. Really, what does specifying mean? This means kind of saying what are the things that are going to affect our demand, quantity demanded. Okay? What did we say in the last equation we looked at would be the effects? We said price, we said income, we said price of related goods. But it could be other things on top of that. So for each one individual, you should kind of go about it and think about what could affect your demand for your particular firm. The second step is then going to be to collect data for the variables in the firm's demand function. Okay, so how would you know what the incomes are of those individuals? You might not know right offhand. You might need to figure that out. Like I always wonder, how does Target, if they use that sort of logic of trying to know income, how do they find it? From what I understand, they take enough information about you, and there's independent places out there that can then estimate what your income is and provide it to Target. Step 3, estimate the firm's demand using ordinary least squared regressions. Okay? The only type of regression we're going to do in this class is an ordinary least squared regression. Okay? So there's no real reason to go too in-depth in learning different types of regressions for now. They're called OLS regressions. They're generally pretty simple. And we did one in the last class. So that would be the final step. Most of the data that you'd see collected for this sort of thing would be time series data, which we went over last class as well. A time series model is going to show how time-ordered sequence of observations on a variable is going to be generated. And the simplest form is linear trend forecasting. Here, sales in each time period QT are assumed to be linearly related to time. So, in other words, what is missing in this little equation? What is something you don't see that you'd expect to see? X is a good answer, or P. Yeah, so we're used to kind of seeing P, right? Next to the B, right? And do we see that? No. So this is saying that the sales in a particular time period, so how much your firm sells, let's say your sales are $40,000 in this year, are assumed to be linearly related to time. What does that mean? That's basically saying that over time, you can almost use a trend analysis to predict where you're going to be next year. You've probably thought of this before on your own. So let's say you're going, I don't know, what's something that has anybody in here tried to run or do something like that before? You tried to beat a time? I'm trying to think of something like that. Maybe not. No? Let's think of a different thing. Maybe studies. Maybe you're trying to get a better grade than you got in the last class. Or you're taking a practice exam. It's probably the best thing. Okay, so you're taking a practice exam. The first time you start out, you take the practice exam, you get a 63. You're like, that's not good enough. I want to do better. And then the next time you take the practice exam, you go up to maybe a 67, so on. But you can kind of feel like the more you're studying, the higher you're going. And the point is that you can almost predict where you're going to be eventually once you have enough data based on your studying habits with the next take. That's what this is saying. Based on where I was with my sales in the past, based on the trend that it has been going in, I can almost predict where it will be in the future. And you can actually run a regression to do that. And that's what they're going to do here. Typically, I go through and actually run the regression with you. And that's not necessary right now, particularly because of the technical difficulties. Okay, so Linear trend forecasting, you're going to use regression analysis to estimate the values of A and B. So that's why they have the little hats on them, A hat and B hat. They are estimated. If the B is greater than 0, sales are increasing over time. That makes sense, right? So if you can envision like a chart where you have an upward sloping sales line, so you'd assume that the next year would be upward sloping too, right? The last point, you'd assume it would go up the next year. If B is less than 0, sales are decreasing over time. So it can work the opposite way too. If it's a downward sloping curve, B is less than 0 and sales would be decreasing over time. And of course, if B is equal to 0, sales would just be flat and constant over time. The statistical significance of a trend is determined by testing B hat or examining the p-value of B, which is what we did last class. We showed you how to go through and look at that parameter's statistical significance. And in fact, that was even one of the questions that we were talking about. Okay, so here's an example of what we were just discussing. Yet you see all these years, and obviously this is very dated data, but you see all these years of data for sales over time. And this is a time series, right? And you see sometimes it goes up a little bit and sometimes it goes down the next year, but on a whole, there's a general trend upwards. And from this, you can fit the line via a regression. And with the regression, now that you fit the line, once you run that regression, you can then actually predict where you will be in the next year based on what you've done in the past. Now see, personally, this is another thing I just saw at work today. People predict things using nonsensical means. This is a good way of forecasting. So, this is something I actually think may be one of the most valuable things that are in this course. If you ever wanted to know how to forecast, this is teaching you how. A lot of people know how to do that scatter plot and then fit the line. I mean, Excel, we showed you last week that you can just do that on your own. But what does the little equation that goes with the line actually mean, and why is it relevant? This is telling you why it's relevant, because now, once you get that little equation, you can then actually forecast based on it. You can forecast outward like that. And I think that that's kind of neat. We're going to show you a little bit of how that can be done from, let's pretend we are in 2006, and we want to know where we're going to be in 2012. Well, we can try to figure that out given some data. So the textbook actually has a different example. In your text, I think it's figure 7.2, where they're going through and they have their sales, again, on the y-axis. We can think of that as your quantity. And on the t-axis, or this is your x-axis, you have time. Now, the interesting thing about how they do this is they have different time periods, and they value each time period as 1, 2, 3, and 4, and so on. So it's actually monthly data that they're working with here. It's January 2007. That's considered time period 1. And February 2007, that's considered time period 2, and so on. So it's just monthly data, and you can envision that April 2008 would be time period 16, and so on. So we don't know what time period 16's value would be, and we don't know what 17 or 18 would be either. The way we can obtain that is to run a regression like that. Run your regression line, and from that, you get this thing called a trend line there. So that's our regression right there. Our regression came out and our y-intercept was 46.57. And if we looked at our regression results, our slope is 4.53, okay? So, by the way, just to give you a quick update on what that actually means. 46.57, that means where it's intersecting that y-axis, right? And you see that? It is right around 46.57 where it's intersecting the y-axis. On top of that, that slope means that on average, it's going up by how much? 4.53. So every year on average, it's going up by about 4.53. Now, sometimes it's different, but just about that. So let's see what this is going to tell us if we then plug in our number 16. So let me explain to you. Generally, I also do this in Excel, but I can't right now. So let me explain to you how you would get the next number. So for number 15, for example, for number 16, for example, you would take 16 and you would plug it in where you see that little t. See that? So it would be 46.57 plus 4.53 times 16. And see what you get. If you do that, you should get 119. So that says that actually this thing is so good that it's predicting that you're going to go down next year. Which actually, sometimes, you have a general trend up. Everybody's going to just say you're going to always keep going up. I think it's sometimes good to be more realistic that you're going to go back to trend. And that's what this is saying. And then it's going to say in period 17, you're going to go up to 123.6. And then by 18, you're up to 128.1. So you get the idea that based on simplistic information, just knowing what your sales are, you can then forecast where they're going to be in the next quarter, the next month, the next year, using this type of logic. All right? So this is how I think a lot of good firms do their forecasting. Rather than just looking at, okay, it's been going up by 4% every year, I assume it's going to go up by 4% next year. That's not the safest way to do things. This is much safer. So, there are some issues, though. So whenever we're talking about forecasting, we should also mention some of the oddities that are out there. For example, let's just imagine that we were just talking about quarterly sales or monthly sales for skiing equipment. Do you think that there would be some problems in our analysis based on that? Yeah, seasonality would be a big issue, right? Because in the winter months, you're going to see much higher sales for skiing equipment. And in the summer months, I'm assuming that it drops significantly. So there's seasonal or cyclical variation that needs to be accounted for. And this can bias the estimation of parameters in linear trend forecasting. To account for such variation, these things called dummy variables are added to a trend equation. I think it's important for you guys to have a general idea of what dummy variables are. I don't think you need to get too in-depth here, but I think it's a good thing for you to know, because you may hear, if you deal with a statistician later on, they may use the term, and this way you have a general idea of what they're talking about. These dummy variables are added to a trend equation. They can shift the line up or down depending on the particular seasonal pattern. And the significance of seasonal behavior is going to be determined using the t-test or p-value for the estimated coefficient on the dummy variable. So let's give you a real quick example. Let's say you have this seasonal trend. As you can see, in period 4, sales jump. So imagine this is like a ski type deal. And for some reason in the winter months, the skiing sales just increase substantially. So our trend would fit that line, but it would fit it a little bit awkwardly because that one month is elevated so highly that it's not going to give us a real true trend. And the dummy variables can adjust for that. They can adjust them up or they can adjust them down, depending on the specifics. So to account for n seasonal time periods, in this case 1, take n minus 1 dummy variables would be added, and each dummy variable would account for 1 seasonal time period. It takes the value of 1 for observations that occurred during the season assigned to the dummy variable. In our example, that would be the winter months. And then it takes the value of z otherwise. So to back up here, you're not going to necessarily see this aspect, I don't think. But you may hear from a statistician later on, maybe in business, and he talks about dummy variables. The thing that I think you should walk away from this knowing is dummy variables are binary. They're 1 or they're 0. They put a 1 on it or they put a 0 on it. And a lot of people just call that dummy variables. That's what they're doing here. And they're using them here for seasonality. So to do that, it may adjust your seasonal line upwards or downwards, depending on certain circumstances. Okay, so some final warnings for this chapter. The further into the future a forecast made, the wider is the confidence interval or region of uncertainty. You guys know this. I know this from weather forecasting. The further out they go with the weather forecasting, the worse the weather forecasting is. That it generally is. I mean, not that it's great as is, but the further out you go, it's just really not very reliable. Same thing with economic forecasting. I mean, economic forecasting is really bad, to be honest with you. So you go out there, you try to predict 5 years from now what's going to happen. It's probably not going to be as likely as there'd be more accuracy predicting what's going to happen a year from now. And that makes sense, right? There's a lot of variables that you don't really know what are going to happen 5 years from now. So keep that in mind. Go ahead, what were you saying? Yep, and the Greek, it is scary. It is scary, and I think nobody really knows what's going to happen there. But that's an interesting thing because you never know when that is going to actually fall. And when it does, I would assume it's going to be bad for the stock market. But unless they bail them out again, and which maybe they can, I don't know what's going to happen. We'll see. But model misspecification is another problem, and this is a situation in which you're not really specifying your model correctly. And this could be done by either excluding an important variable or using an inappropriate functional form, and it can reduce the reliability of a forecast. Forecasts are incapable of predicting sharp changes that occur because of structural changes in the market. That's kind of something that we're just discussing with the Greece situation. All right, so that's the end of Chapter 7. I'm going to try to figure out how to turn off, bear with me for a second here.